Okay, great. Hi, everyone. Thanks for coming to my talk. So I think today I want to talk about something that we have been working on together about essentially around open source models and also about building infrastructure for generative AI, right? So, generative AI and the language model is a really crazy field, right? So time moves really, really fast, right? It's hard to imagine once upon a time, there's a time that there's no llama, right? That feels like forever ago, right? But if you really think about it, it's not really that far away, right? So probably like 1 year old, right? So this field has been moving really crazy speed. And we have been making a huge amount of progress if you look at open source as a community. So we helped to run the first version of Helm, right? So this was the model that we had back then, right? As a whole community. So there's a first generation of the models, right? So people start to do this, right, in the open back in 2021, 2022, and then you see the second generation of models, right? So if you look at today, right, so and the community make a huge amount of progress. So if you look at Helm today, right, so you can see in the top 6, there's already a single open model there, which is kind of fascinating, right? They start to have open models become somehow like this alternative to closed model, right? So there's still a gap between open and closed, but open model become essentially somehow useful. So despite all of those progress, there are also challenges that we are facing as a community. So I will argue there are essentially two parts, right? So there's the data and also there's compute. So on the data part, right, so I think the community have made a huge amount of progress in getting great data sets, Pal, C4, the stack, all of those. But on the other hand, what's actually missing is first on the data recipes missing, right? So how can we map this raw data set into a high quality core that can maximize the model quality, and how can we clean them, how can we mix them, and how can we reproduce a recipe given a new domain, right? If you have some application, you can build a language model on your own for your own specific application, how can you think about data? And what is the systematic process to create a data set that fit your application? We have no idea how to do that. And the diversity of data is also lacking. If you look at what's in the open, right? So, and the community actually get really good at internet data because of a common crawl, really good at code because GitHub's there, right? And really good at producing synthetic data, right? Try to do alpaca style kind of distillation, right? From a strong language model into a weaker one. It makes a huge amount of progress. But is there any other way to connect more data and more diverse data source with open model build? That's something that I think the community need to figure it out. There are also challenges on the compute side, right? So if you look back in the last year, the community managed to get computation resources that actually make many of the projects actually possible, but the availability of compute is still hindering the progress, right? So there's a low availability of compute at a very high price. It's very amazing how much progress you can make when you give top researchers just a few GPU and burn them for a month. But even that is not something that everyone have today. So another way to look at this availability problem is there's a very strong requirement on the infrastructure to get anything done. When we talk about infrastructure for language model, we are thinking about, those machines are being connected by 3 terabits network, right? And part of the availability challenge is actually coming from our requirement on what is usable for doing anything about language model. And reuse is lacking. Right? If you look at 2023 and think about, okay, how many models, like 7 billion models that we train as a community for 2 trillion tokens, there's an embarrassing amount of them, right? Probably we train like 10 of those models. We probably have enough amount of compute to burn on them that train an even larger one, right? But somehow people are building those smaller artifacts without really coordinating with each other, without reusing what people have, right? So I think there's a whole bunch of challenges that actually fascinate us, right? Both on the company side, but also on the academic side. And we have no idea how to solve any of those. So, and I think those questions will probably be understood by the community better. And we really want to be essentially part of that and try to help in whatever way that we can. So if you look at data and compute, right, so it's not surprising that this will be the main challenges that facing the community, because data and compute are really what's really driving the community for the last decade. So this is one of the figure in one of the OpenAI paper, right? So this is scaling law, right? As you can see on the left-hand side, the more data you push into the system, the better the quality of the model you are going to get. But of course, you are not just burning the compute for nothing, right? So the more data you put in, right, the more compute you are going to burn, but the better the model you are going to get. So because of a phenomenon like this, if you look back history and say, okay, what is the data set we are using for machine learning? We actually went a long way, right? We went all the way from back like 10 years ago. The biggest data set we have as a community is ImageNet, 1.3 million images. All the way to today, we start to put billions of images into the training process. And on the other hand, the compute start to explode, right? If you want to do a GPT-3 style kind of like a recipe, and we are talking about a couple thousand GPU running nonstop for months, and that doesn't even give you the most expensive model that you can train today. So, and because of this tension between data and compute, the way that we think about where we can make our contribution is by thinking about the space as the tension between essentially three different players. So the root cause of the problem, also opportunity, coming from the data part, right? Data get larger, get more complex, the quality of the data start to decrease, the amount of cost you need to pay to clean the data, to acquire new data start to increase. As a consequence of that, the models start to get more complex, get larger, and both the model and data start to essentially add in pressure to the infrastructure. You start to require a huge amount of storage to serve the model, huge amount of floating point operations to actually train the model. And as a reaction to that, the infrastructure start to evolve essentially in two different ways. So first one is start to specialize. That's why we see all those like tensor core, right? All those like specialized accelerator for those models. And second is start to scale out. So what we are very excited about is essentially how to close this loop. What we believe is if you want to make the whole thing like 100 times cheaper and faster in the next 10 years, what you need to do is not to innovate on one of the player, because at some point you are going to meet this like diminishing return at that dimension. What we really want to do is to figure out how can we connect the three different players and have them essentially compound together for a longer period of time. And that is essentially what we are very excited about. So our belief is on the infrastructure side, fundamentally is going to decide the fundamental cost of compute and data movement. And the model architecture and the algorithm to do decoding, to do training, is going to define the fundamental limit about the utilization of the infrastructure. That's like the percentage of the hardware you can actually use. And data will essentially be the power coming from the competitive side and also decide the requirement on the compute and the data movement. So the goal is really try to have all those dimensions come together, and hopefully we can find the right balance between these three different dimensions as a community. So again, we have no idea how to solve any of those problems, how to have them compound. That's what we are going to figure out together with the community for the next 10 years, I think. But there's also some of the smaller projects we are making moving toward that direction. So on the data part, right, so one thing that we are very excited about is really try to figure out data and also data recipe that essentially map data quality all the way to model quality in a principled, reproducible, and scalable way. We have been doing a couple projects, right, so under the name Red Pajama, right, I'll talk a little bit about today. So on the model side, the thing that we are very excited about is how can we bring those like non-transformer architecture from research to production. Right, we have been building models like Striped Hyena and the Mamba, right? So and we are learning during the process about how to connect model and data and how to enable non-transformer architecture. And on the infrastructure side, we are very excited about how to essentially improve the economics. How can we do joint optimization between system, the kernel, communication, architecture, right? Tree have this amazing kernel like fast attention, fast decoding, right? So how can we design algorithms, right? How can we fit the model architecture into the infrastructure to make sure it's easier to inference or training, and how can we co-design all the way from algorithm, model, and system and hardware. So that's something we are very, very excited about. So we haven't just like closed this loop. We are essentially trying to work with the community to try to innovate at each of these dimensions. So today I will talk a little bit about essentially each of those, right? So on the data side, one thing that we have been doing and very excited about is this project called Red Pajama, right? It contains like 30 trillion tokens, and what's actually more interesting, in addition to the token count, is actually give you this modular view of data quality, right? So I will explain a little bit, later. So if you look back history, right? So and think about the Llama 1 moment, which feel like years ago, but it's not that far away. So what's really enabled by this model, it's not really only that it's a good model. It is a good model. But I think fundamentally more important at that moment is Llama is really the moment that the community got hope. It's that it's actually possible to build an open model that's great. So, and that's actually inspired us like 1 year ago, right? Essentially we say, okay, so, I mean, how can we reproduce Llama, right? Llama has this great paper, have a whole bunch of data recipe, right? But they never reproduce, they never release the data and they never release the code to actually produce the data set they're using. So the first version of Red Pajama, essentially we say, okay, let's try to do a best effort Llama reproduction. So we read the paper really carefully and try to reproduce every single data slice and apply the same filter as described in the paper as careful as possible. So it's a data set with like 1.2 trillion tokens, right? So have 7 data slices all the way from internet data, C4, right? GitHub, archive books, Wikipedia, and Stack Exchange. So this is the first version. It's got a lot of attention from the community, and what we are very proud of is, if you look at many of the open models, they all have some red pajama-ness in it. And what makes us really proud is people start to build over this data set. For example, Cerebrus have this very interesting data set called the Slim Pajama, right? Which is a kind of deduplicated version of Red Pajama, and which enables a whole bunch of other models, right? Including some of the models that we built. So it's kind of very exciting to see, right, a single data set produced in a rather simple way can actually make some difference to the community. But on the other hand, there are also something that we kind of keep learning, right, after we have the data. So there are multiple lessons that we learn. The first one is being able to flexibly twist your data recipe is more important. So what is the degree of deduplication? What is different filter criteria? What is the combination of those filters? All of those are kind of important. They might be even more important than pushing out a single data set. Having the process to be something that the community can build on is actually more important. And second, how can you systematically map data quality to model quality is a really open problem. I don't think anyone have any idea how to do that systematically. So if you want to build another data set, it might be more useful to actually build out a framework to help the community to explore data quality than just release another golden data set and claim that it works everywhere. So that's essentially what we learned. And that also inspired the second version of Red Pajama. So essentially, in that data set, we process every single common crawl dump, right? Passing through the CCNet pipeline. It gives you like 100 trillion tokens. In fact, we kind of pick 5 languages that we have expertise on, right? So that's essentially this 100 trillion raw token. And then what we do is we do a very basic minimal filtering, right? We just do exact deduplication and bring the whole thing down 30 trillion tokens. And what's even more interesting is, in addition to the essential raw token, we also overlay like 40 different quality signals, right? To really say, okay, so this is how good this token is in this perspective. Some of them are just heuristics, right? So for example, you can say, oh, Wikipedia is a high quality data set. What is the similarity between this document to Wikipedia, right? You can actually use that to do filtering. And there's a whole bunch of quality rules that we get from all of those papers. There's a whole bunch of fuzzy deduplication signals. You can essentially try to deduplicate yourself at different degree. So, and then we also keep the format consistent with DOMA, right? If you're using DOMA to do data processing, we hope it's going to become a drop-in replacement of some of the data set, right? You do not need to, so essentially we hope to make sure we can reuse our code, reuse our data as a community. What the whole thing actually enables is you have a single data set, but there are essentially 40 different ways that you can look at the data. So these are the histogram of every single quality signal, right? Right? I mean, you can see kind of very interesting, right? You can actually slice and dice the data in very different ways, right? You can actually combine all those filters in very different ways. And what this enables is actually it could provide a modular view of data quality. And here's what I mean by that. So if you think, okay, if you like the golfer paper, right, say, oh, so that's a very good data quality filter, you can just reproduce the whole thing in probably 20 lines of code, right? So we have enough amount of data quality signal for you to reproduce the golfer data set. I mean, that's the best effort reproduction. Of course, not going to be exactly the same, but it's kind of the best effort. If you like C4, if you like red pajama V1, you can reproduce them in a very simple way. And what is code enabled, which we have no idea how to do, is in principle, you could start to combine all those filters, use across different papers, all the way into a single data set, like a data processing pipeline. And in principle, you could automatically learn that. We have no idea how to do that, but hopefully someone smart is going to figure that out using the data set that we produce. So that's the hope. So this is essentially on the data part, right? So now you have 30 trillion tokens, a whole bunch of essentially data quality signals. And what's the next thing I really want to share with you is some of the model building effort that we have. So we built a model called Striped Hyena, right? So, and the goal is really try to understand how can we push the frontier of non-transformer models. What is the hypothesis we have in mind? The hypothesis we have in mind is, can we have an alternative architecture match the top modern transformer in quality? We are not talking about having like a non-transformer model that in principle matches transformer on a small data set or like 1 trillion tokens. We want to have an alternative architecture that matches the best, right? So that's the goal. So, and here's where we get started. So essentially, it's kind of a very interesting architecture. Actually, the paper is out today on archive. So essentially, you have, what we have done is we take the transformer architecture, a whole bunch of layers, right? So, and we kind of replace some of the layers with a hyena layer, right? Which is long convolution, right? So, and then we do a whole bunch of distillation, right? We take a very strong model and we try to essentially bring them into this hybrid architecture. And then we did a kind of data recipe like in red pajama and then continue pre-train the whole thing for a while, right? So, I mean, it's a very simple process. But what's actually interesting is to start to say, okay, it's actually possible for you to get a model that's actually good, right? So here's what I mean. So if you measure like short context applications, right? So it's only 2 points lower than Mistral, which is a very, very strong baseline, right? And then you can actually continue to fine-tune the whole thing, right? So that's the time you are going to get a model that give you essentially better quality than Mistral at a short context. So this first time, probably someone actually showed that. And second, if you measure long context applications, right? So it's also essentially give you better quality on those. So, and this give you benefit on the infrastructure side, right? So like if you look at end-to-end latency, the x-axis is the context length. So you can see when we are doing really long context, like 128,000, you see this like almost 2 times improvement on the latency of the query, and also it uses essentially like almost 2 times fewer amount of memory compared with a pure transformer-based architecture. So it has, I mean, if not better, but comparable quality for both short context and long context. And on the other hand, it actually gives you real benefit coming from the infrastructure side. So there's some early lessons that we learned, right? So first one is, I think the biggest thing that we learn is alternative architectures can actually give you state-of-the-art against the strongest transformer-based that we can find at the time. And second, it can actually give you real benefit, right? So that can be measured in real inference time that's actually optimized, right? So this is the real serving platform that people are using, and you can actually provide additional benefit on the essential state-of-the-art, right? Instead of some like slower version of the transformer. So there's so much to do, right? Like in this perspective, but what really gets us excited and really want to share with the community is there's hope, right? I don't think we find the right way to train the model. I don't think we find the right architecture. But what we actually excited about is that thing is possible. I'm pretty sure if the community come together and spend time on it, right? So we are going to come up with non-transformer architecture that's actually become alternative to transformers. So that's what makes us really, really excited. So what's actually even more exciting on the more academic side is this alternative architecture start to open up a different dimension of the scaling law, right? So here you can actually mix a different amount of attention and the hyena layer, right? And you can see instead of have a single line in the scaling law, you have two lines, right? Because now you can change how many non-transformerness you have in the model. And for different type of mixture of attention and non-transformer layers, you start to see, yeah, so it is possible for you to have some architecture that have a better scaling behavior if your scaling is measured by model quality versus flops, right? So it's kind of interesting. And then you can play with different degree of mixturing, right? So on the left-hand side is 100% transformer. On the right-hand side is essentially 100% hyena, right? So, and this is essentially the best that transformer architecture can actually achieve, this line, right? So, and you can see, yeah, it's actually possible to have a pond that's actually below this line, which means that you can actually have quality benefit given the same amount of compute by essentially mixing architecture together. So there's a paper just get on arXiv today, just like, I think like 2 hours ago, right? So have more details about this. So this is essentially the model building effort, right? So we are doing a little bit more, but I think this is something that we are very, very excited to actually share with everyone. So another thing that we are trying to figure out as a company, also as a research group, is how can we figure out the economics of serving and the training? So this is, if you go to our website, right? So this is essentially the cost of inference today, right? So yeah, it's usually like 10 cents to $1 per million token. But this is just the beginning, right? I don't think we converge on pricing. I don't think we converge on speed. So the fundamental belief that we have is today we are counting token by millions. The day will come that we count token actually by billion, not by million. So I think that's going to be the world that we are going to live in a couple years. So, and that's our dream, right? If you look at some of the model, right? For example, LlamaGuard on the platform, yeah, we already start to count token by billion, right? But I think the day will come that all of those models, for both inference and training, the tokens will be measured in billion, not billion. So there's this like 10 to 1,000 times improvement of cost and speed that we are going to. Yeah, I mean, if we fast forward 5 years, I think that's what's going to talk about. So about infrastructure, right? So always based on your belief of the future, right? If you look at system research, fundamentally we are trying to imagine what the computer is going to look like in 5 years and try to build for it. So fundamentally, I think there are two things that we are very excited about on the infrastructure side, right? This kind of two trend. That is, there's this concurrent aggregation and disaggregation happening for the infrastructure. And I think that's going to give us a huge amount of opportunity in cost optimization. On the aggregation side, right? So if you look at data center as a computer, if you look at like within every single rack, every single machine, right? So within a data center, there's this continuous trend of aggregation happening. So this was a A100 GPU, right? If you look at the memory hierarchy, yeah, I mean, there's a HBM, right? So there's a CPU memory connected by PCIe, right? So it totally charges like 20 gigabytes per second. But this is not GPU looks like today. If you look at GH200, right, what's actually fascinating is they start to have this fabrics between CPU and GPU, which communicate like 900 gigabytes per second. It's amazing. And it's not really this fancy GPU. If you have an M2 Ultra, right, you start to have this like 800 gigabyte links between CPU and GPU. Because of the memory system and because of how machines are being connected by the network, there is this very drastic trend of aggregation happening at the data center scale. On the other hand, there's also disaggregation happening across different data centers. If you look at the cloud, they are already essentially disaggregated, right? So GCP is just like have data center everywhere. And if you look at the GPU cloud, right? So there are reasons that it could be even more disaggregated, right? So there's a constraint of power consumption, right? If you look at DGX box, it actually use a lot of power. There are environmental factors, there's a cost, right? There's limited supply, right? And sometimes just easier to scale kind of when you have a disaggregated view of the whole infrastructure. So fundamentally, something that we believe in is there's going to be this continual trend of disaggregation happening essentially across data centers. And that's going to give you different things, right? So within a machine, one thing that we are very excited about because of this view of aggregation is essentially how can we optimize data movement across the whole stack, right? Because the whole thing is going to be aggregated, data movement will become cheaper, and potentially that can enable things that you can actually not do today. For example, one paper a little bit on the crazy side called FlexGen, essentially we try to do very optimal, well, not very optimal, but near optimal kind of CPU and GPU offloading for inference, right? You can do a 70 billion model inference at high throughput mode, right, on a 4090, right? So, and imagine you have the PCIe speed 10 times faster, and that thing start to become useful. There are a whole bunch of things you can do, try to optimize data movement, which is the opportunity opened up by this aggregation trend. And across data centers, right, so because of the disaggregation happening, so one thing that we are very excited about is how can we compress data movement across different kind of data centers, right? If you can bring this like global scale disaggregated data center as a single cloud, I think we are going to open up something that we cannot even imagine today. So from the technology side, right, so this is something we are very, very excited about. So I will just like talk a little bit on the disaggregated side, right, which is about communication compression, right? So just like one dimension of the infrastructure thing that we have been doing, both in the company, also as a research group. So we all complain that the compute is kind of not there, but actually compute is actually there. So if you look at how many flops you need to do a 175 billion private model for 300 billion tokens, this is actually how many flops. It kind of looks like a lot unless you realize, no. I mean, if you look at this like folding at the home projects, right? So they have is the same amount of compute in 2 days if you only measure flops. So the availability of flops is not really the bottleneck. I mean, they are there. Was actually fundamental, and I would even go one step further to argue the community even figure out how to incentivize people to actually provide compute, right? If the community will say, okay, let's try to build a model of the same scale, compute is not the problem. So what's actually the problem is this gap, right? On one hand, if you look at data center network, we are talking about like 100 gigabits to 3 terabits. But if you look at those like kind of disaggregated compute, we are talking about this. There's this like 1,000 times communication gap of the bandwidth, and also this vast heterogeneity of devices and network. So that's the fundamental thing. It's not we don't have compute, it's we don't have a compute connected in a way that we are able to fully utilize every single flow that we have in the device. That's fundamental. And this is not really a not only a problem for the disaggregated part. So this is one of the runs that we have been running in one of the biggest data center in the world. So as you can see on the x-axis, right? So this is how many GPU you have for the training, right? So the green curve is the ideal case, and the blue curve is actually a real run. It doesn't look like a big gap, right? Unless you realize, oh, I mean, that's gap that looks very small, actually means more than 500 GPU are being idle during the whole training process. Not because the GPU is not good, but because the communication start to get in the way of scaling. So communication is a bottleneck across the whole kind of spectrum of infrastructure, from data center to multi-cloud to serverless environment to distributed network. The way you are moving from left to the right, you have a slower network, even though you have the same amount of aggregated compute. And the thing that we kind of very excited about is how can you move a workload all the way from the left to essentially to the right-hand side. Because the belief is that if you can move a workload from left-hand side to the right-hand side, you start to open up more choices for the user, and fundamentally, that could become cheaper. So that's essentially one thing that we have been looking at almost in the last 10 years. And here's what we learned, right? If you think about the neural network, about the training side, right, it's a whole bunch of layers or loss layer in the end. When you do training, right, you have a data set, you draw a sample, and essentially do two things. You do a forward pass, and then you compute the loss function. Then you do a backward pass, right? You compute the gradient of every single layer. So And then like you don't want to do this like one data point at a time. You want to essentially parallelize it, right? So and then you have this like data parallel training. You have this multiple parallel data sets cannot do this like in parallel. And then the model might be too big, doesn't fit into a single device. Then you start to cut them into different pieces, right? And you can see this like 3 different communication channels for distributed learning. So there's a communication you need to do. We want to do the forward pass. Communication you need to do. We want to do the backward pass. And communication you need to do when you exchange the model gradient of the same layer. So one thing that we learned in the last 10 years is essentially it is possible to design a single algorithm that all of those communication channels are compressed in a very aggressive way. So you need to kind of do a different algorithm for different channels because they have different statistical property, but there exists a single algorithm that all of this can be compressed. That's one thing that we learned after looking at the compression scene for 10 years. So, I mean, the algorithm is kind of interesting, right? So, like, this is one of the interesting called LGD that we had published like last year at NeurIPS. So, it's kind of try to combine a whole bunch of compression techniques. But what's actually interesting is these are the convergence curve, right? So, it's a 6 billion model and 20 billion model for fine-tuning. The y-axis is training loss, the lower the better. The x-axis is essentially the training iterations. So as you can see, essentially the blue curve is essentially full precision all radios, right? So, and the green curve is what you could have when you compress the data parallel channel by like 100 times, right? So as you can see, right, so even though we are compressing communication by 100 times, you are getting almost the same convergence behavior out of this, right? So, and if you do some naive way to do compression, right, you do see the gap, right? So what's actually interesting is kind of you start to run this over slow network, right? So here, right, so like, as you can see, right, the y-axis is throughput. Like, even though you could have, for example, very slow network, like 500 megabits network, I mean, after 100 time compression of the communication, you will get almost the same throughput as if you are running the whole thing in the most powerful data center in the world, right? So essentially data parallel training over 1 gigabits is actually possible. And you can actually do more, right? Because every single channel can be compressed. There's another paper we have last year on NeurIPS. So this is actually, you do a 3-bit forward, 6-bit backward, and 4-bit data parallel gradient exchange. And we cut the model into 8 different pieces. So and something crazy that we have done is, yeah, we start to put these 8 different pieces in 8 different cities that are connected by a pretty fast network yeah, for this geo-distributed setting, right? So from essentially 500 megabits to like 1.4 gigabits. But it's possible. It's a real decentralized network. And as you can see, right, so like even though you are training the whole thing in a kind of slower network, you are getting like 1.5 times slowdown at most compared with 100 gigabits network, right? So that actually makes us very excited because there are this like additional dimension you can play with when you design infrastructure. This is not all we do, right? This very simple dimension, right? And we are doing a whole bunch of things over this for both inference and training, right? And for different quality requirement of the user. Sometimes you cannot compromise quality, sometimes you can, right? So, but what gets us really excited is not how great this algorithm is, right? It's essentially there are additional dimensions that you can actually play with by changing the algorithm, changing the model, changing the software, that in our opinion is going to bring down the cost for the next 10 years by another 10 to 100 times. So that's something that we deeply believe in. It's going to take the whole community to actually make it happen, but I think it's something that essentially this is the right moment to actually study those. So this is actually all I have for today, right? So just like share with you some of the things that we have been working on, right, at different dimensions. And over the years, we are getting a lot of help from the community, essentially for every single one of those projects. So all of them are collaborations with the community, and we are learning like a huge amount, yeah, from our friends. And yeah, hope to continue to do that. Yeah, so that's actually all I have.